Welcome to Ask and Learn.
Here's an example with the gravitational force and adding forces as force vectors. So we need to find the net force or the sum of the forces on the mass in the center of a square with different masses placed around. And just as a reminder, the gravitational force is an attractive force uh, and goes as the product of two masses over their separation squared along a line joining the two masses. And we want to fill that in a little bit more carefully. But we can see that everything is the same with the force on that mass in the center, except for the mass it's interacting with. But let me kind of show some forces. Due to force 1, we want to join a line. And the gravitational force due to mass 1 is along that line. So we'll call that force 1. Force 2 is going to go, of course, on a line to number 2, and it's going to be twice the size in magnitude. And likewise, force 3 is going to be along a line with the third mass, and 3 times long. I think I drew the second one a little bit too long. 3 times the length of the original F1, at least in magnitude. Its direction is different. And then finally, we have force 4, which is 4 times longer. And we can kind of look at these in pairs and see, kind of get a sense for what the x and y components are going to be doing. So if we kind of divide, how to say this, divide top and bottom, what we can immediately see is that the net force is going to be downwards, quite substantially downwards. And that's because the two upwards forces are not as strong as the downward forces. However, we can also tell that the F sub x net is pretty much going to cancel itself out. And the way we can see that is that there's a difference of 1 unit of x component to the right, because the difference between the masses is 1. And there's a difference in the x component to the left of 1, because again, the mass difference between those two masses is the same. So what we can tell is that mainly it's the y component, of force is going to wind up with a net non-zero portion. This is usually good, is to try to use some sort of symmetry or eyeball the forces, and you can often save yourself some work. Now the y component for all of those forces, let me just draw one out. So here's a force. And its y component is going to be the magnitude times the sine of 45 degrees. And that'll be either a plus or minus sine of 45 degrees, depending on whether the arrow points up or down. So sine of 45 degrees is the square root of 2 over 2. Fairly easy thing to do. Okay, so let's go ahead and write down the y components of our different forces. And we'll see that there's a common thing that winds up in the magnitude. But F1y is g times m squared over the distance squared, by the way, is we can look at our square, which has a side of a. So let me kind of draw a little aside here. Each side has a. And what the separation is for each of these is basically a over 2 plus a over 2 added in quadrature with a Pythagorean theorem. And that winds up to be the square root of 2, a over 2, not surprisingly. Okay, so we want to put that in for our r squared, so that's 2/4 a squared. And for the first force, the y component is positive. And that's all we need to do. The second one, we have 2 gm squared, and the separation is still the same. And we have another positive y component. F3y, now we're going to get into the negative components. And yeah, we'll simplify that in a little bit. And finally, the fourth mass is pulling down as well. And I see that I can simplify all of these. The 2/4 a squared is really the same as 1/2. And the 1/2 cancels the 2 in the square root of 2. So we can simplify things down just a little bit more. And so finally, the sum of all the fy's is equal to gm squared over a squared. There's a square root of 2 in common with them all. And then let's see, we have 1 plus 2 minus 3 minus 4, which is, all said and done, minus 4 square root 2 gm squared over a squared. And that is the net force. As we said, the sum of fx is 0.